Are the notes online?
Yeah, so
Okay.
they'll be posted later, so on Wednesday, but then I also record live on YouTube,
Okay.
so you can watch the rest of it there.
Thank you. I appreciate it.
Also, who turned in their homework to me in lab today? Because I have one, it's a no name. So if you were the first person to turn in your homework in lab, yeah. I try to learn some of your handwritings, but with 22 of y'all, and I just met you. So yeah, if you have stuff to turn in, you can just make piles of lab and homework, and you can give it to me at the end of class too, no rush. All right, I guess we can officially start. So again, just so we're all on the same page, so I don't check your homework for accuracy, I just check it for completion, although I will try to like scan and maybe like point out a few things if I notice an error. But you want to go ahead and check your answers. So right, we have our homework answers, and this is there as a PDF file. So you can, kind of check, and there may be, discrepancies potentially. For example, people already brought like vinegar to my attention. So vinegar is also acetic acid, and so they were kind of going for more like the supermarket vinegar, since it's technically, right, dilute acetic acid with a bunch of water. But stuff like that, just kind of check. And again, I'll let you kind of go through this, but the answers are there for you. And then, of course, if you have questions, right, I'm more than happy to help you. But that's how homework works. So you'll get, 10 points for completion grade. I'll try to point out errors if I see them, but there are many of you and one of me. And then I think everybody is registered. I probably sent out a few emails to people individually if you were not in a lab lecture recitation section. So just again, double check your registration, and I'll probably go through my roster tonight. But just if you have questions, if you're not signed up, just talk to me. But I think it was only 2 people missing from my recitation. And I'll just write a reminder. So we need lab, lecture, and recitation. So you need all 3 for your complete, right, 5-credit chem package. Any other questions or housekeeping things that we need to go over before we dive into chemistry? All right, so let's start talking about the second chapter. And of course, ask questions. And so we'll try to go slow on this second chapter. So we want to build really good foundations And then this will help us as we continue throughout the course. And so now we're just introducing elements again. So we had kind of briefly touched on elements, at least when we're talking about classification. And we have our periodic tables. Again, if you need an extra one, I have some, I'll leave them here. You've already lost yours. And so we established, right, anything on this periodic table. This is an element or an atom, right, so it cannot be broken down. It's just our definition of an element. So again, it's just a pure substance. And of course, don't forget things in its elemental form. And so this is just a reminder, right, don't forget your diatomics. So do we remember our diatomics? What were those? Or can we name one of them? What do we remember?
One of them is hydrogen.
So hydrogen, yes, that was one of your diatomics. Hopefully you already have them circled. Nitrogen, and I'll go ahead and circle, right, remember all these, oops, as I go crooked. So all these were our diatomics, and again, all we're saying is that they're a pure substance, and yes, in their elemental form, they're found as bonded, which seems funny, but they cannot exist just on their own. So for example, right, you wouldn't just find a neutral chlorine in nature. So I'll put not found. So that's what it means with our diatomics. And don't forget, right, other substances. So we talked about the allotropes, so you kind of remember, right, graphite, diamond. So all those we said were still elements. And so your book just wants to put kind of the elements in context with your body. And of course, right, we are carbon-based life forms. Does anybody know why we're carbon-based life forms? There's a few things about carbon. So carbon has a much smaller radius than you would expect. And so because of that, it can also do a bunch of bondings, and so carbon can bond with itself. So silicon can't do that like carbon does, so carbon can make all sorts of rings. It can triple, double bond too, not only with itself, but other elements. And again, we'll kind of talk about that. So of course, we expect to have a lot of carbon in our body. And notice we also have a lot of oxygen. And so, of course, oxygen is found in water, so that's going to be in our body. Obviously, we have a lot of water by mass. And so, of course, with that, right, again, we're organics essentially. So hydrogen would also be high on the list. And then you have nitrogen. So, of course, nitrogen is also in, like, your amino acids and a bunch of other organic compounds. And then it starts dropping off, but, right, we need all these other ions too. So what are ions good for in the body? What do they help with? Why do we need ions? So hydrated. So going on with that, so why do we need ions to stay hydrated? Why do we drink Gatorade? What do those ions do? What are some of the physical manifestations of a lack of ions? So somewhat related to hydration, but we want that hydration to bring ions. And this also goes into like the pure water that you're drinking right now. So water, right, is not actually just pure water, so it has ions in it. So there's trace, sodium, potassium, whatever in there. Maybe if you're drinking Dasani, they put other flavors in there like sodium bicarbonate, different things to kind of give it that flavor. But what do we need ions for in our body? So what happens if you don't have ions and you're not hydrated? You get dehydrated, yeah, but then what are the physical symptoms? What do we need our ions for? So then we'll start feeling some like probably low energy or cramping, right? And so I was thinking of kind of the cramping, because when your legs start to cramp, that usually means you need ions. So sometimes they say, right, eat a banana. Well, why are you eating a banana? It's because you want that potassium. And so you need those ions to help transmit like electrical synapses, right? Like magnesium is super important for your heart's electrical function. So you have to think about, right, how your body works. And so, just to move, your body has to send, right, an electrical impulse from your brain to your fingers out there. And well, how does that electrical signal travel? Well, it has to go through a bunch of ions in your body. And so, right, when you start depleting those ions and you start cramping or having, right, physical manifestations, maybe feeling, right, low energy. So that's what you need your ions for. So keep all those electrical impulses flowing, all those chemical reactions going, right? You're one just big equilibrium of chemical reactions. And so all these metals, even though they're a small percentage, obviously they're really important. And then we have other kind of trace metals in here that it doesn't mention, but we probably need, right? Manganese, don't forget iron in your hemoglobin, and several others that failing to mention. But again, right, you don't need to know this, just big picture, right, we're carbon-based life forms, so mainly oxygen, hydrogen, carbon, and then, right, we need those ions to transmit our electrical impulses. And so we also want to look at, well, how do chemists communicate? And so chemists, you'll quickly realize they use a bunch of shorthand all the time, a bunch of weird pictures. So we have to be comfortable kind of interpreting them. And so this is just our kind of ball and stick model here. And so in this case, does anybody know what element or what compound this is trying to show? So water, exactly. And so, right, we could redraw water like this, so probably more familiar with that. And so red usually stands for oxygen, and then the white is always hydrogen. Black, you'll look at as carbon. Blue tends to be nitrogen. Yellow, sulfur. Halogens are green. Oops. And again, not trying to overwhelm people, but at least just provide kind of a guide. And so this one, you want to be able to translate, again, to kind of rewrite it like this using our chemical symbols. So again, the black one we said was carbon, and then these white balls are H's, so hydrogen. Right now I'm not drawing in 3D. Then we have another carbon. So this is one other way to draw it. And so this is what I say this is what I mean when I say, like, let's draw it explicitly. So if I say draw it explicitly, then we show all our hydrogens. And again, you'll later learn that I always joke that chemists are lazy, but right, chemists always, again, use a bunch of symbols. So the other way to show this is literally just a line. So that means the same thing. And so how that translates, each point is going to be a carbon. And then the rule with these organic structures, you might want to write this. So carbon needs 4 bonds. And so, right, they don't have to be 4 separate bonds. So sometimes it could be a double bond, but it needs 4 lines coming out from it. And again, you'll have some practice. And so that's why when you draw this, kind of retranslate it, well, there has to be a carbon on each end. So we said each point or each corner is a carbon. And then we said, well, carbon needs 4 bonds. And so since nothing else is drawn, it's implied that there are those hydrogens to fill it in. So kind of confusing when you first see that, but oops. Sorry, let me move this. So let's just look at other examples. So let's compare. So we could draw this versus that versus this. And these are, yes, they're all structures, right? They mean different compounds. And so we said, we already translated what this one meant. But see if you can translate and draw out the structure of these last two. So draw it out right explicitly. So filling in the hydrogens. And you know there has to be 4 bonds. So just take a minute or so, try to draw it, and then we'll go over it. And for the second one, so we should have gotten, so again, each point is a carbon. So you have a carbon with a double bond here. But then we said, oh, carbon needs 4 bonds. So this one needs, right, 2 hydrogens attached to it. Same with this other one. And then our last one, right, that's a carbon triple bond. So carbon triple bonded to itself. Again, carbon needs 4 bonds. So don't forget that last H. And then what you should start seeing is also how these little structures start to tell us the 3D shape. And let's actually pull them up so we can see it a little bit better. So let's go back. And so in the lab, you'll kind of play with the little molecular model kits. But again, going back to ethane, right, you can see how it has 3D shape here. Each of these carbons are what we would call tetrahedral. Again, we'll get there in the chapter of identifying geometry. But this also tells us, again, a little bit about how it behaves based upon its structure. And so that's ethane. And you don't have to know how to name these, so these are organic naming. Again, this is kind of just for your introduction. And where did my windows go? And so if we look at either ethene. So this would be its IUPAC name, or its common name is ethylene. So carbon with our double bond. But now we can see it has different 3D geometry, and so you can tell by this structure that it is flat, so it's totally planar. You can also tell that by how the carbons are, and again, we'll go into that as we progress through the course. And then comparing it with, so this is the proper IUPAC name is ethine, but it's more commonly used as acetylene, so you may have heard of acetylene gas, especially if you're like welding or something. And again, right, you can tell this is obviously linear now, so kind of a small molecule. So ethene, ethine, I'll put acet, and I can't spell, acetylene. And so again, that's something that we'll be practicing as we go throughout the course, is what does this look like when we draw it on the paper, but what does that mean kind of in its 3D shape in real life? How does structure dictate reactivity? So other things we should look at. So we can look at benzene. So benzene, this is just an organic molecule. So the formula is C6H6. And I'll write it out. And so the funny thing about benzene, first I'll write it how a chemist will write it. So a chemist usually abbreviates benzene like this. And so let's translate what the heck are they trying to tell us. And so of course we know each point is a carbon. So all those are carbons. So now I'm going to start redrawing it more explicitly so we all know what's going on. All right, so I have my 6 carbons. And then they have this funny ring here, which this means delocalized pi, but what this is really just trying to show for our purposes is alternating double bonds. And again, what this ring means is we can write the double bonds in different positions, and it's the same. So I can redraw these double bonds. And so I'll just shift them now. And again, they mean the same thing, so that's what this little ring means. And then the last part, well, we said carbon has to have 4 bonds. And so 1, 2, 3, and so all of them have a hydrogen attached. Now we can see where the formula came from. I'll draw them on here as well. And then again, eventually we'll start seeing that this is a planar structure. And so another skill that we want to acquire throughout this course is being able to look at this picture then and write the formula for it. And so what is, right, the molecular formula? And so I'll give people a second to at least attempt to go through it. And so remember, this is a carbon, so there's going to be a carbon on this end, and carbon needs 4 bonds, so don't forget that. So I'll give people a few minutes. So try to rewrite this maybe explicitly. So don't forget, right, that's a carbon. So where are all your carbons? And usually the order is carbon, hydrogen, oxygen, and then heteroatoms. So I'll just leave that space. Do we have guesses? Are we still working? So at least highlight, so write all your carbons that aren't drawn out. And so once you do that, then you got to start filling in, right, the hydrogens that should be there, but again, since chemists use what I call shorthands or they don't draw it out. So this is, right, a carbon with 3 hydrogens then. This one's a carbon with 3 hydrogens. And then we have this carbon, so 1, 2, 3. So it has 1 H on it. Then double check these, so 1, 2, 3, 4. So this one's okay, right? There's no hydrogens on it. But then this is another methyl group. This is a carbon, so 1, 2, 3, 4, that's fine. And then don't forget this one, again, 1, 2, 3, 4. This one's 1, 2, 3, 4. So let's hear it. What do we get? How many carbons do we get? 8. What do you think? 8? Everybody get 8? So you could count them. 1, 2, 3, 4, 5, 6, 7, 8. That looks good. And then how many hydrogens? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And what about this one? So do we get 9, 10, 10? So it should be 10, so don't forget about that one. And then how many oxygens? Right, 4 oxygens? So how many oxygens? So 2, and then how many nitrogens? 4. Any questions on this one? Do we want to do another one? Does anybody know what this molecule is by any chance? So this one's caffeine. Okay. Do we want to do another practice? Let's try another one. So how are we coming along? So of course, right, we have all our carbons. And so I'll probably just draw the hydrogens to fill it in, knowing that all our, again, our vertices are carbons. And then of course, right, this is a carbon, but it has no hydrogen on there. And then how many hydrogens are on this carbon? 2. And then what about this carbon? How many hydrogens? So 1. So usually people forget about these guys. And of course our methyl group. And so note, right, if a hydrogen is attached to any other element, so right, nitrogen, oxygen, they are going to go ahead and draw it out for you. So it's only when it's attached to the carbon that you have to go back and fill it in. And so what do we get for our formula? So how many carbons do we have? So 6, 7, 8, 9, 10. How many hydrogens? Oh, let's see. Heard all sorts of. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that what people got? I totally could have miscounted. And looks like we just need nitrogen. So how many nitrogens? So 1. So you don't have to put a little subscript for 1. And then, so a fun fact, anybody know what this chemical is? Any guesses? Yeah. So it is methamphetamine. And not to get too much into the legality or illegality of drugs, but right, all that separates methamphetamine from amphetamine is literally that little methyl group. And so that methyl group right there just makes it a lot easier for meth to cross that blood-brain barrier, and so that makes it a lot more potent. So, you know, that's why it's more illegal, but again, not to go down the rabbit hole of like why Ritalin, for example, right, that's basically amphetamine, so that's given as a prescription versus meth. Anyways, it's all about the dosage. And so other fun facts, so this is for like drug chemists. And so again, methyl groups are pretty favorable, but also what's analogous, and this may be surprising, is a fluorine group. So sometimes adding fluorine can help make drugs cross that blood-brain barrier. So you have, like for example, let's look at Prozac, which I can never pronounce its chemical name, so this fluoxetine. Let's pull up the Wikipedia page. But, right, this, for example, has this trifluoromethyl group here. So, again, that would probably help it cross that blood-brain barrier. So, just something that chemists think about when they're, you know, designing drugs or trying to make different classes of drugs. So, kind of altering the methyl groups or adding fluorine. So, those are interesting groups for chemists. All right, so now we'll start kind of looking at our periodic table. What is it telling us? And so let's start with our atomic structure. And so you may know this, but atoms are all composed of the same subatomic particles, so protons, neutrons, and electrons, so just in differing amounts. And so the first thing you'll notice, and so we have, right, the mass of the proton and the neutron are nearly identical. And so this is basically 1 AMU. And so usually we say the mass of the electron is negligible, so we don't really care. So when we add up our masses, we usually just add up our protons plus our neutrons to give us our atomic mass. And so electrons are relevant, though, in their charge. And so you may be aware that the proton and the electron have opposite charges. And so, right, the proton we formally sign as positive, and then the electron is formally assigned as negative. And again, they have equal charges, but just opposites. And then, of course, neutron, right, neutral, so it has no charge. And so this is, again, kind of our quick handy-dandy chart. So we don't really care too much about their mass in kilograms, at least not with the calculations we'll be doing. But we do care that, yes, a proton is about 1 AMU, a neutron is about 1, and then our electron is negligible. So I'll just put 1. So again, for your purposes, you'll just be rounding, and that is 0. And then again, here's the charge. So if you cared, right, the charge of an individual electron is 1.6 times 10 to the negative 19. That was found doing the Millikan oil drop experiment, so that was pretty cool. They dropped some oil, suspended it, and then calculated, right, the electrical field that was needed to suspend that drop of oil, and calculated how many electrons were in that oil. And that calculation has held. That was pretty fascinating. All right, so now let's get to the important stuff. And so this is super important, and you probably want to highlight it. And so the elements are defined by their number of protons. And so anytime you're looking at the periodic table, right, it says the atomic number up there, at least in yours in the upper left corner. And so again, that atomic number is the proton. And so we can say equals the atomic number. And so if you change the number of protons, and again, that would only happen in like a nuclear reaction, right? That's when you start losing protons, neutrons, and things start changing identity. But that's what changes the element. That's what defines the element. So again, just circle that. So your protons defines your element, right? So all hydrogens have 1 proton. And we'll learn that we can have different isotopes of hydrogen. So there's regular hydrogen, there's deuterium, there's tritium, but all 1 proton. And so sometimes we say that the atomic number is also called Z. So that may come up in like your homework terminology. And so again, we can see that they're arranged by their atomic element, or atomic number. And so I'll just look at this periodic table. So of course, right, 1, 2, 3, 4, 5, 6, going in order. So as we kind of take a second tour of the periodic table, we'll look at kind of why they're in these rows and columns. But again, we're getting there. And so again, we'll see this. So we're kind of like dancing around all these topics right now. So that's what you kind of find with chemistry, is like there's a lot of information in the beginning. So if you've never had chemistry, you might be clueless, right? But again, just kind of hang with me and build and ask questions. And so again, we'll figure out that elements within the same column have similar physical and chemical properties. But again, we haven't explained why yet. We're just kind of, this is what's happening, but we're getting there. So we're slowly getting there. And so again, we have their symbol. And so in general, so in this case, right, you have your atomic symbol. And so you can see from your table that's either a 1-letter symbol or sometimes a 2. Yeah. Oh, sorry. I can zoom out too. And then usually, and so it depends how it's written. So sometimes we'll look at isotopes. So this would be for an isotope. And so you're looking at kind of the smaller numbers. So this, and how it's written, is going to be the mass. So mass. And in this case, we're just looking at 1 isotope. And again, what's an isotope? We're getting there. And then the smaller number is our atomic number here. Or also, right, our protons. So that's one way to write it, so you might see that. And so now we've been kind of touching on this, but not. So does anybody know some isotopes? What are they used for? Have we heard of isotopes? So they give some here, but what are other isotopes that we might be familiar with? You don't have any favorite isotopes? Or any isotopes? So let's look at carbon. So most people, at least once we start talking about carbon, they'll remember. All right, so we have carbon. And so let's just look. So the most common isotope is carbon-12. And so again, this is another way to kind of write isotopes. And so in this case, we're just given the total mass. And again, you can go back to your periodic table. So let's go back to this one. Okay, we look at carbon, atomic number 6. So I know it has 6 protons. And so let's put that, so we have protons and neutrons. We'll put electrons in there, but right now we're not changing electrons. So we're just looking at neutral carbon. So of course it has 6 protons, right? Again, I just got that from the periodic table. It's atomic number. I'll show it again. I just want to make sure everyone's following. And then so neutrons, well, how do we get that? And again, we've kind of danced around this, but let's clearly define it now. And so for each little isotope, right, our total mass of our atom then is equal to our number of protons plus neutrons. And so right now, we're again just in atomic mass units. We're just adding everything. So how many neutrons does carbon-12 have? So I heard a 6 whispered. And so 6 neutrons exactly. And then it's neutral. And so in a neutral substance, the charge, the number of electrons has to equal the protons. I'll put 6 here. And I'll go ahead and write our mathematical formula. But basically our charge is equal to, now I always say protons plus electrons, but right, electrons have a negative charge. So if you need to like subtract in your brain or whatever you need to do, so I'll write it, so number of protons plus number of electrons, but again, you're really adding a negative to that. And so again, our charge is 0 for neutral, so that's why they're the same. So does anybody know the other 2 isotopes of carbon? Any guesses? So what are the other 2 main ones? No guesses? So neon, we'll look at neon later, so looking at its isotopes. But an isotope, right, it would have to still be carbon-based, because isotopes, again, would be same element, just different neutrons. So what are other carbon isotopes? No, we don't know any. So carbon-13 and carbon-14 are the next 2. So carbon-13, I wouldn't necessarily expect y'all to know about. And so, right, it still has 6 protons. How many neutrons does carbon-13 have, though? So 7 exactly, so we can do the math. So we have a 13 total for the mass. So all that's changed is we have another neutron. And so, right, electrons are still 6, so it's still neutral. And so carbon-13, and this is why I wouldn't expect you to know it. So this is used for what's called NMR. So it gives you like a pretty picture of the molecule. And so now this is probably like going too far. And so carbon NMR is kind of difficult to capture. And again, now I'm probably giving too much information, but because it's difficult because our carbon-13 nucleus is only about 1%. So basically, right, you stick your sample into the machine, but you're only looking at like 1% of it trying to detect it. So that's why it takes a long time. And that's compared to, again, giving too much information, but like normally you look at a proton NMR, and that's almost about 100% abundance. I'll put like 99%. So that gives you like an easy, quick picture. And so we're talking about like seconds to collect versus minutes on how long it takes. All right, so again, you probably wouldn't care about that one. But let's look at carbon-14. You might be familiar with it. So how many neutrons would carbon-14 have? 8. So excellent. How many electrons?
6.
And so carbon-14 is radioactive, and so it's used in carbon dating. And let's see. Its half-life, it's about like 5,730 question mark. That's probably wrong. Something like that. So about 5,000, 6,000 years for the half-life. And so you can measure, I think, to around 60,000 years ago or so. Again, kind of plus or minus depending. And so now we can look at another example of isotopes. And so kind of the other fun thing about isotopes is, right now I'm just kind of throwing all this information at you. But honestly, so scientists don't know, why isotopes exist necessarily, or why some are like radioactive versus stable. And so that's something, again, if you get really bored, you can look at the chart of nuclides in our lab, or you can Google some on the internet and you can knock yourself out looking at all the isotopes. But kind of, common trends you notice, if the protons and the neutrons are close together, like they have about the same amount, that generally means that's more stable. And so again, right, we don't know exactly why, but now once we have this imbalance and kind of more neutrons than protons, that makes the nucleus kind of unstable and again radioactive. But then you'll notice if you go to like heavier elements, it's very common to have a lot more neutrons than protons. So it's kind of a cool phenomenon. And so again, now we can look at neon. So this is another way to write it. And they have their atomic number all on bottom. And so then you can just figure out the number of neutrons. So of course, this one has 10 neutrons, 11 neutrons, and 12 neutrons. Questions about isotopes so far? I just don't want to move too fast. And so again, this is just reiterates how we get our mass. And so again, mass is just protons plus neutrons. And so again, just another way to write it. So you might see 35 chlorine. And so sometimes they put the atomic number, sometimes they don't. But that's why you always have your periodic table. So, okay, let me look at chlorine. Oh, there it is, atomic number 17. Then you can either fill that in or get your other information. And so again, this is just another way to note it. So just kind of be aware. That's what they're trying to tell you when they start doing these weird, chemical name plus numbers. It's usually some sort of isotope. So see if you can practice writing this symbol then. So what's your atomic number, mass number, and symbol of a chlorine isotope with 18 neutrons? We'll give everybody a minute or so. So walk me through the pieces. So what do you get for the atomic number for chlorine?
35.
So what's the atomic number though? Because 35, right, is our mass. But then that's mass of just one isotope. So 17. And so what's the mass number of this one? It could be the mass on the periodic table, but what's our mass number? Or how do we get that too? So what do we get for mass? So 35, and again, right, that's just your protons plus your neutrons, aka your atomic number. So we had 17, and then it told us, well, it had 18 neutrons. And so now I can start writing. So 35, 17, and then what's the symbol for chlorine?
CL.
So Cl. And then, so when we look at ions, we would also put the charge in this corner. So in this case, it's neutral, so we don't need to put a 0 or anything, just kind of leave that as such. Let's see. Let's at least talk about, before I start going into stuff, so let's go over ions before I forget. So now, well, what are ions? And so ions are any sort of charged then atom. And so they could be both positive or negative. And so if it's positive, we call it a cation. And so people usually remember, because that little T kind of looks like a plus sign. And then, of course, negative is anion. And so let's practice kind of writing them and figuring out what they mean. So let's say we have this symbol here. So take a few moments. So how many protons does it have? Neutrons and electrons. So consult your neighbor if you need, your friend. So let's start, so how many protons do we have? So 20, so good, right? And again, we get that from the periodic table, so we said our protons defines our elements, okay? That's a good start with 20. And so now, what's the number of neutrons? What did you say? 24. And again, you just got that from our formula. So our total mass, right, equals protons plus neutrons. And then how many electrons do we have? Yeah, I don't know. 18, exactly. And so there's a few different ways to think about it, right? You could start with the neutral. Well, I know the neutral has 20, but then it's a plus charge, so and electrons are negative, so we're probably losing some. Or we could do the math. And so, right, I would say, well, we have a 2 plus charge, and that's equal to my protons plus my electrons. But again, electrons are negative. And so then, again, just setting up the algebra, so 20 plus x is equal to plus 2. And I'll distribute that negative sign. And so minus 20. All right, so now you get negative 18 equals negative x, so x equals 18. So whichever way you see it, again, whether you have to start from the neutral and then add or subtract, or you could, again, set up the algebra. Let's do another isotope practice with charges. So let's do, so that's 81 bromine. And so it just has a little negative charge. So you could either write just a little negative like that or write -1, so same thing. Just a -1 charge on it. And so same thing, protons, neutrons, electrons. What do you think? So what do we get? How many protons does bromine have?
35.
So 35. So again, once again, we get that from our periodic table, so it's a good place to start. How many neutrons do we have?
46.
So 46, so good. Everyone did 81 minus 35, excellent. Then how many electrons? So 36. So excellent. So again, you could start from the neutral. So you know the neutral is 35, but then if it's an extra negative charge, you add 1. Or again, you could set up the algebra equals 35 minus x, and then you get x equals 36 as well. All right, one last little point before we start looking at the periodic table and running all around is, so you'll notice, so let's look at this one. And so let's say we're looking at our masses, and so one thing that maybe is funny is, well, these masses are weird decimal points, and we just finished saying that, right, our masses are basically whole numbers of each atom that we're looking at. And so let's look at bromine as a good example. And so the mass on your periodic table says 79.9 roughly. And so mass of bromine, again, this is from table. So 79.9. But then the funny thing is, well, there's no bromine isotope that's 80. So you have a bromine isotope that's 79 and 81. So where the heck does this mass come from? And so the answer is, so this mass, again, on your periodic table, so this is going to be the average atomic mass then of your isotopes. And so what I mean by that, and why I picked bromine as a good example, is, well, I just finished saying there's no bromine 80, but bromine's pretty funny in that it has these two isotopes, and they're basically in about a 50% abundance. And so the proper formula is then, right, your mass, again, on your periodic table, so your average mass, is just equal to the sum, and again, this looks complicated, but we'll break it down. So you would have, right, the mass of isotope 1 times, right, the percent abundance in decimal form. And then, right, you just keep adding up until you have all the masses averaged, right? So mass then of isotope 2 times your percent abundance of isotope 2, right? And then you just keep going. And so what this basically means for bromine is that we have, and again, I'm just going to take kind of the rounded one. So let's just say we're at 79 AMU for isotope 1 of bromine. And I said they're about 50% abundance. I'm not going to look up the exact numbers. So of course, right, you would probably have more precise both atomic mass and percent abundance if you're actually doing this. So just doing a quick rough calculation. And so again, just doing a rough calculation, we're going to get 80. Sorry, I forgot to pull up my calculator. And so right now we just add up. So 79 times 0.5 plus 81 times 0.5. Again, just a rough estimate. And we get about 80, right, which is, again, right about what our periodic table got. So again, if we use the actual numbers and actually looked up, you know, all our sig figs, we would get what the periodic table got, but this is basically the process. So you see approximately 80 AMU. So that is where those numbers come from. So again, note that this corresponds to your average, right, not one individual isotope. All right, I think, so do we feel okay about isotopes and ions for now? And so the rest of the chapter is starting to kind of look at the periodic table. How is it arranged? What are all these elements? What do they look like? And so let's start doing that. And so I like this one website, assuming I can pull it back up. There we go. So this is just ptable.com, but why I like it is that at least has, this used to pop out a lot nicer, but it kind of gives a Wikipedia link to it, and I really want to see the pretty picture, but I guess we have to click on it now. And so let's start doing that. So let's start looking at our groups. And so of course, note hydrogen is kind of our odd man out over here. So it's put under here since it has one valence electron, which we'll look into. Well, what the heck is a valence electron? But again, just starting there. And so if we look, most of these are the alkali metals. And so this periodic table is color-coded, but you may want to write this down. So our alkali metals. And do people know what property, what kind of unifies the alkali metals? What are they known for? Yeah, they blow up, right? So they blow up in water. So we say right there, water reactive. And of course, the reactivity increases as we go down. So kind of looking at some things. So we're kind of, again, touching on things, but I don't want to overwhelm people. But as we go down each row, right, we keep adding more and more shells. And so all that means is as we add more shells, so let's say we're looking at like cesium. So cesium, that valence electron is all the way out there. And so that makes cesium super reactive. And I'm sure you've seen some videos, probably in lab, or either in lab or in class. I need to figure this out. But we will play with lithium, sodium. I have to see if we have potassium on hand or not. But potassium is always kind of the limit of what you can work in air. So rubidium, you can't. Potassium, though, does have that potential to autoignite. And so back to our periodic table. So again, these are all metals, and they're all shiny. So I have to click on them now. They used to just pop up so pretty. It's kind of irritating. And so again, they are nice and shiny. And so that's only when they're freshly cut. And so when we play with this, we'll look at this again. But right now, this is the unreacted surface. And then right away, it's going to start oxidizing. And so usually when you look at these samples, they have this white poopy stuff all over it. And that's just, right, metal oxides just forming on there. And so again, you go down. This is not as fast as I want it to be. So here's some potassium. And notice how a lot of these are stored in mineral oil. So that's to protect it from the water. And so rubidium, now rubidium is stored in an ampule. And so to use this, you would probably pump your ampule into a glove box, which is just, you've kind of seen like those NASA things where it's like a giant box. Google a glove box. But it's just a little box of an inert atmosphere. So usually nitrogen, if you're Gucci, sometimes you use argon. And so the only reason for that is nitrogen does actually react with lithium. So nitrogen is pretty unreactive, except it makes lithium nitride. So lithium starts to take a blue sheen once it reacts with nitrogen. And then again, going down, so then you have cesium. So this is, again, pretty explosive. You can find YouTube videos of people usually smashing ampules of cesium or rubidium, and they just immediately blow up. And then francium is radioactive, and so you can see it has less data on it. And so again, it's radioactive. And so you can see, again, getting a sense, you get those larger elements now, they just become more inherently unstable. So this only has a half-life of 22 minutes. And so that's why it has that funny mass. So notice, right, its mass is not really well known since it doesn't live long enough. And of course, you can kind of appreciate, so we don't usually talk about these synthetic elements, but again, you can appreciate that's why they have not very well-defined masses. And then, of course, everyone's in a race to name them, whatever cool thing. All right, so now moving over. So now this is, right, our alkali earth metals. Alkaline earth, sorry. And so these also tend to be water reactive, but less so. So usually I say they're acid reactive. So they kind of need a little bit more to make them go. So you have beryllium, magnesium, calcium, strontium. And again, they're all metallic-y looking. So let's look at calcium. So again, nice and shiny. So we'll look at samples in lab at some point. And again, you'll notice that they get that white poopy crust stuff. And again, that's just calcium oxides reacting. So strontium, again, shiny metal. And again, reactivity increases as you go down from our shells. And so then in the middle, we have the fun part. And so this is the transition metals. So we won't focus on them too much in here, but basically they're responsible for all the pretty colors, especially in fireworks. So a lot of these are transition metals, or I don't know if y'all have ever played with like those fire salts before. They sell those, like turn your campfire different colors. Yeah, and they're just different salts. So a lot of them are copper salts, and copper gives that nice green. And we'll be doing flame tests. Now I don't remember which week. But we do have flame tests coming up. I'm trying to pull up your syllabus. So you'll be burning elements and getting their colors. So we'll skip transition metals for the most part, just because they're funky. Again, what we just want to appreciate is, yes, they are metals. So again, let's just look at one for an example. I don't know why the internet always gets so slow. Internet. Come on, chromium, we just want to look at how shiny you are. Let's try another one. No, none of these want to work. And so a lot of research, too, is devoted in the transition metal arena. Oh, here's finally manganese, so you can appreciate, right, it's shiny, it's metally. So we'll keep marching over. And so now this is kind of group 3. So we have boron, aluminum, gallium, and indium, and thallium, of course, in this row. And so this is an odd one. And so notice, right, boron starts your semi-metals, so all this stair step. And so a lot of these semi-metals can be used as semiconductors. So, right, silicon is used in chips, trying to use germanium as well. And then we have just our metals here, so aluminum, gallium, indium, tin, of course. Thallium, fun fact, is super toxic, so you wouldn't want to work with thallium salts. They can also lead to like hair loss if you become poisoned with thallium. Tin is also super toxic. Again, that would be compounds of tin, so not elemental tin. But tin compounds are pretty toxic, can cause convulsions. And so this stair step is also kind of our dividing line as we go from metals to now non-metals. So again, right, all these are basically metals on the left side of the stair step. And so now crossing into our non-metals. So we can look at group 4 first. So group 4 over here. So of course that's carbon, silicon, germanium, and tin and lead. And so carbon is just black. So this could also be, sometimes people call it like charcoal. And then have y'all eaten like those black ice cream cones or anything? And so a lot of you've had the black ice cream cone? It's gross. Did it taste gross? Well, it shouldn't taste like much, but yeah, the carbon, so like the black stuff is really just carbon or like activated carbon. But I would put out like a word of caution. So do people know, because you can use, and again, people use these terms interchangeably, they really shouldn't be, but like activated carbon or that charcoal, because have you seen that like cleansing products for your face or sometimes toothpaste? And so the idea with that activated carbon is that the carbon can basically suck up impurities. It's also used in chemistry to kind of help purify compounds. It's supposed to like bind to the impurities. But you have to think about that if you're eating a bunch of activated carbon, that could potentially make you sick because it's also like, you know, binding to anything you ate. So we just mentioned, right, we need a bunch of electrolytes, but maybe the activated carbon's sucking out the electrolytes. So it can do weird things. But I also have heard some people eat the activated carbon to like help with like allergens. So it's all, right, everything. The dosage makes the poison. So you don't want to overdo the activated carbon thing. Obviously, if you eat too much and you feel sick afterwards, maybe that's why you're sucking out something that you need. But anyways, that's how it works, and that's where it comes from. So just be careful with your carbon eating. And so let's look at silicon. And so there was a paper a couple of years ago where some scientist was trying to claim that they found the first silicon-based life forms. There was a big news about it, but then it turns out they, I think, lied. And so still haven't found any silicon-based life forms. And so moving to germanium. So again, germanium's on that stair step, so kind of this metalloid. And tin, so you probably know tin, so tin's metally. And so now let's look at kind of group 5 over here, so it doesn't really have too special of a name. So nitrogen, phosphorus, arsenic, and antimony, and of course bismuth down there. But just focusing, so of course nitrogen, and at some point I will bring liquid nitrogen to play with. But this is liquid nitrogen, so of course condensed down, and at some point we'll have to make ice cream or something. So phosphorus, I think we went over phosphorus when we were looking at allotropes. So again, now we can tell definitely non-metal, right? It looks like a non-metal, different powdery substance. And then so arsenic is under the stair step, so back to being a metal. Oh, come on. So there's just arsenic for reference, the metalloid. And so group 6, I like to call the smelly elements. And so, right, oxygen isn't smelly, but oxygen, eventually I'll have to condense it for you. So oxygen is actually blue as a liquid. So you condense it, you would see. And so this is also a safety hazard, though, if you were doing like organic chemistry. So it's fine in our purposes, and when I do it, it would be fine. But you would not want to mix oxygen with an organic solvent or something, so that would be a bomb. And this is a hazard that's associated with doing glove box chemistry. So anytime you're doing kind of this inert atmospheric chemistry, if you have a leak in your system and you're pulling a vacuum, which is usually how this happens, is you're trying to evaporate solvent and then you have a leak. Next thing you know, you suck in a bunch of liquid oxygen, and if that combines again with that organic solvent you pulled off, that can go off. And so if you were doing that kind of chemistry, that would be a cause for a lab evacuation. You just close your fume hood, you let all your lab mates know you condense oxygen, and then everybody leaves for the day. And you hope the vacuum pump just carries it away. But you wouldn't want to mess with it, because then you trying to take down the trap can cause the explosion. Let's see. And then so moving down, so sulfur is where we start getting smelly. And so you might be aware, so of course hydrogen sulfide is smelly. They also put in, so they put in mercaptan. So that's what makes natural gas actually smell. So it would otherwise be odorless, so you can't detect it, but you can smell this mercaptan pretty easily. And then so moving down, so selenium is also smelly. So this would be, if you were exposed to it, you might have like an onion breath or something weird. Let's see it. I think Wikipedia mentions it. So yeah, they're kind of toxic and smelly. So not good. And then moving down, so tellurium is even smellier. Let's see. Yeah, so they said it has a radish odor. And yeah, so a lot of smelly things. Here we go. So yeah, tellurium poisoning. So yeah, so you can also have that tellurium breath, and again, you'd have a garlicky breath, and that would not be good. And so then let's finish up. So let's look at our halogens down at the end. So halogens, so let's look at them. So of course these tend to be either gases or fun solids. So we have fluorine. So fluorine's pretty nasty. So this is liquid fluorine condensed. And so usually fluorine, if you were working with it, you have to have like a special regulator since it's pretty toxic and corrosive. And so some fluorine chemists do that though, where they add like fluorine gas to their reaction. So not fun. And so chlorine is again also a gas. And so sometimes chemists kind of make this chlorine gas and then we'll add it to a reaction if you need. And although friendlier reagents, so once you get down to bromine, so bromine is a brown liquid. And so bromine is used a lot in organic synthesis, so it's good as a leaving group, but it's also a nice reagent because now it's in a liquid form, so you can just pipette it in. And it is angry and fuming, but it's still easier to work with than a gas. And then iodine, we'll look at some crystals in lab. Oops, I didn't want fluorine, I want iodine. Why do you keep changing? irritating. Ha. So this is iodine. So iodine's nice and pretty. So it kind of looks like violet or something, all these purple shiny crystals. And then what's also cool about iodine is it's sublime, so it goes from a solid to a gas, and then it'll recrystallize on like the top of its vial. So sometimes you can see little purple iodine crystals at the top of a vial. And this is the same iodine that's used in like disinfection in hospitals, but of course that's more dilute in the solution form of iodine. And iodine is a controlled substance, so you can make meth with iodine, but again, you can make meth with a lot of things. So now that leaves us with our noble gases at the end. So our noble gases are generally unreactive, but of course, chemists would want to force it to be reactive. That's the name of chemistry. And so we have neon, of course. And we have a few neon lamps in labs, so we'll look at those. And you just pass electricity through that, of course, causes the electrons to be excited. Of course, now I think all those lamps are going out of favor. There's so many LEDs now that are cheap. And so again, argon, so just showing them kind of in their gaseous form with electrons going through them. So krypton, that's cool. All right, so that's just kind of our general tour. What are the elements? What do they look like? But now we want to take a second tour, and we want to look at electronic structure. Again, we want to go slow with this to ask questions, but we want to start to figure out, well, why are they also arranged in this kind of funny pattern here? And we'll kind of look at electron configuration with this, which I think is next chapter, but if we kind of introduce everything now, it'll hopefully make sense because they're all related. So let's start back at hydrogen. And so now we're going to go back and, well, what do these rows even mean? And so we're just corresponding to our first shell, and I'm going to write 1s here. And so 1s, again, so we'll write both our electron configuration, but then let's also, before we jump too far ahead, so our s orbital just looks like a nice little ball here, so just kind of your basic onion ring. And then we want to write our electron configuration, so it's going to be 1s1. And so we can write a couple of things as well. So this is going to be known as our S block as we kind of keep moving forward. So S block. And so if we notice our s orbitals, so they're too wide on our periodic table. And this means that each s orbital can hold 2 electrons total. And so let's also translate that. So you might be familiar with what I call our oversimplified version of our electronic orbitals. And so, right, you might have this n equals 1 with 2 electrons. Does that kind of look familiar from school previously, where you have like this 2, then what is it? It's like 2, 10, 18, 36. Does this look familiar to people? So now we're kind of going to rederive this because this is oversimplified, but we're going to understand where the heck these numbers come from, what do they mean. And so usually with these, at least the principal number falls in with them. That should be 8. 2, 8. And so all this means, so this is our first shell. So, sorry, this is our first shell. So this is just corresponding to this first row right here. So our 1s. And so we can also, why I like this is we can go over to electrons. And so it does kind of split it a little funny. So it's trying to help you. But now let's click on hydrogen. And so notice, right, it tells us our electron configuration. And so it just has 1 electron. So 1s, 1 there. So just like we wrote. And so now we can go over to helium. So we're just kind of going to go in order for now. So helium, so now we've filled up our S. And again, this is also kind of funny. So we have helium over here, right, hanging out with our noble gas. And why it's over here, it's because it's generally unreactive, right? And so we can go ahead and write our electron configuration for helium. So it would be 1s2. But now we want to really explain, well, why is it unreactive? Why is it happy with 2? And so have y'all heard of the octet rule before? So we'll get to the octet rule. But usually people say, oh yeah, the octet rule. And so that's basically when an element has 8 electrons, it's happy, but we'll kind of see when this applies, when it doesn't apply. But if we look at helium, right, well, helium only has a 1s. Jeez. So helium only has a 1s. And so we say it's satisfied by the duet rule. And so hydrogen would also apply. So right, once hydrogen has 2 electrons, now it's happy. So now we're kind of explaining, but not really, why it's bonded to itself. So again, we can say duet rule. And so all we're saying is that its first shell, so our 1s shell, right, is completely occupied. And so again, the duet rule only applies to hydrogen and helium. All right, so now let's go down to the next row here. So we're just going along in order, right? We just looked at hydrogen, helium. So now we're at lithium. But now we've started a new row, which means we have a whole new shell. So now this is going to be our 2s starting here. And so notice the 2s, so we'll fill up these two. So first we're going to fill up, right, our s orbital. But now, once we're at our second energy level, we have our p block will be next. So this is 2p. So this will be invoked. And so now I'll kind of highlight all this. So this is all our p block here. And well, what the heck is a p orbital? And so let's look at, well, what is a p orbital? So there are 3 p orbitals. And so I'm going to call this PZ. I have different shading. So PZ, PX, and then PY is coming in and out of the plane of the board. And so we usually say that there are 3 p orbitals, and so you can kind of draw them like this. I'll fill this back in for our s orbital. But each one of these suborbitals can have 2 electrons. So right, each p, so you would fill, of course, 1 in each energy level first, then go back and repeat. So we say this p orbital can hold 6 total electrons, again in our p. So going back to this, so notice the p block is 1, 2, 3, 4, 5, 6 across. So that matches, right, with how many total electrons can fit in there. And so let's first go back. So let's write our electron configuration for lithium. And so with electron configuration, right, you always start from the beginning. You have to fill up from our lowest energy levels. So that's why we always start with our 1s. And then you just go through it in order. And so you might want to make some markings here. So this is 1s. Now we start 2s. And so, right, we just fill across. So 1s, 2. And then we continue. So now this is 2s. And then this is 1 here. And so starting to see a pattern. And so now this goes back to reactivity. So all of these, right, are going to end in NS1. So saying, right, all of these have 1 valence electron in that outermost S shell, whatever that is. So eventually we'll get there, right, 3s, 4s, 5s, 6s, 7s. We can always double check ourselves again on this P table. So just for clarity, so looking, so we can click on lithium. And so again, right, it fills it. So notice how it has it, the lowest energy level down at the bottom. And then the next one is 2s. So again, 3 electrons for lithium. So you start filling the lowest energy level first. And then our next one, so 1 and then 2s. So following so far. And so then we can look at beryllium. So let's just keep going in order explicitly. So beryllium, right, that would be 1s2, 2s2. And then while we're writing it, so you may have learned you can also abbreviate this. And so what we do is we can go back to our previous noble gas. So in this case, right, we haven't gotten very far. So we're looking at lithium. Our previous noble gas is helium. So we could also write the electron configuration as helium, 2s2 for beryllium here. And so again, this little symbol just means we're going to start with the electron configuration of helium. And of course, right, we already wrote it as 1s2. And then we'll just go from there. All right, so now let's do boron. And so let's do boron. And so now 1s2, 2s2, and now we're still in the 2s, right? So it's now 2p1. And I'll write it in a couple of different ways. So again, just get used to other ways of seeing this. So we could write 2p, 2s, 1s. So this would be another way to write this information. So 5 electrons, I'm going to start from the bottom. So 1, 2, 3, 4, and then 5. And so again, note how I write the arrows. So the electrons are usually denoted as these little half arrows. And so we're kind of getting there, but haven't officially said it. And so why I write it like this is because we can't have an electron occupying the same space. And well, what the heck does that mean? And so it's basically a quantum mechanic rule, but I can't write this. So this would mean that these two electrons are literally occupying the same space. So mathematically, that doesn't work. So one has to be what we call formally spin up, which is denoted like this, and the other spin down. Sometimes you see this notated by little numbers. So this is like quantum numbers where you have a half spin and then a negative half spin. But again, for our purposes, we just care. That's why we write it kind of one up, one down like that. And that little half arrow notation. All right, so now we've answered this question as well, of why this was 2. So now this is 8, since this corresponds to our second energy level. And so that's going to be 2s plus 2p. So 6 plus 2 gives us 8. So that's where that number comes from. It's just now we're breaking it down into s and p orbitals. And so let's just kind of continue. And so again, right, we'll kind of start noticing a pattern. So this was NP1, NP2, NP3. So they'll have similar endings, right? That's why they're in these rows. And these endings, aka the number of valence electrons, is what's dictating their reactivity. So NP6. So let's write down, let's do nitrogen's electron configuration. So take a minute, see if you can write it out for yourself, and then we'll go over it. All right, let's hear what you got. So somebody start us off. So do we want to use abbreviated, or we want to start with the 1s? What do we do?
Will you accept both on the test?
Yep, so I would accept both. So what do you write?
I tried with abbreviated, but I don't know if it's right.
So yeah, so start us off. So what'd you do?
I did HE and then 2P3.
So HE, and then you said 2P3, but just don't forget, so, right, that's a good ending for nitrogen. But, so we start with helium, and so just going in order, so we got to write 2s, and then so 2s1, 2s2, then we get to 2p. So don't forget that. Oops. So 2s2. And so a good way to double check yourself is you can add up the little superscripts plus whatever you started with, and they should equal to your atomic number. So right, helium is 2, and then so plus 2 plus 3, and so that gives us 7, And again, double checking, well, nitrogen is 7, so that matches. And again, we're looking at neutral, so all that works out. And so other things that we were kind of touching on. And so notice, right, every time you start your new row, so these would be, now it's called your valence electrons, or your outermost. And then you had a question?
I was just wondering if you could write it like without the abbreviated part.
Yep, and so we can also write it, so 1s2, which is the same electron configuration as helium, and then 2s2, 2p3. Again, we could write it in our other forms. So again, we'll keep practicing with this. I know we're starting to run out of time, but we could write it in this form. So we need 7 electrons. So 1, 2, 3, 4, 5, 6, 7. So it looks something like this. And so one last few notes and thoughts to think about is we also want to translate this to what's called our Lewis dot structure. So these are going to be our valence electrons, and we'll probably reteach it from what you're used to, but I would say call each one of these a side of your little Lewis dot structure, right? So this can be my 2s, my 2p's, right, because we have 3 2p orbitals, and then I'm just going to fill in exactly what this looks like, except in terms of dots, or again, I'll rewrite it for clarity. So we'll end on this, but don't be overwhelmed if you have like no idea what I just drew. So we're going to keep going through electron configuration slowly, working our way through the periodic table, but then looking at these funky symbols and what the heck they're telling us. So again, ask questions. I know it might be a lot of new information, but we're trying to build up everything together so you kind of learn everything and it makes sense. All right, I'll stop yammering and I'll stop this stream. I'll accept homework and then I'll answer any questions.